Now for that second question. If a neutrino has an abundance of empty space to pass through, then how does the detector even see a neutrino? I wonder if it has something to do with those lousy odds of a neutrino hitting an atom's nucleus.
It's even worse than that, because not only would the neutrino have to hit that nucleus, which is 100,000th the size of a whole atom. In the nucleus, there are protons and neutrons, and they're composed of quarks. And the neutrino only interacts by the weak force, which has a range of about 1/1000th the size of the nucleus. So it has to not only nail that really tiny bullseye in the middle of the empty space. The bullseye itself is 1,000 times too small, and it has to hit that. And so when a neutrino is so incredibly unlucky as to just drill some quarks so dead on, it knocks particles loose that are normal and have charges and leave tracks in our detector, and we can see what's going on. And the way we do that is we look at the neutrino comes in, gets really, really unlucky, blows stuff, splat. We never see the neutrino. Our neutrino detectors never actually see neutrinos. They see the debris from a neutrino blowing something up. And so we reconstruct that debris and point back to where the neutrino was, in the same way as if someone was playing a game of pool, but the cue ball was invisible. You could have a pretty good idea where the shot came from by watching the break, and that's the game we play.
All right. I decided to do that too, but play the game in the literal sense. So I went to Tycoon's Zenith Ale House and Eatery in downtown Duluth, and I tried my hand at knocking around a few neutrinos. This cue ball will represent a neutrino. Down at the other end is a group of billiard balls that represent the nucleus of an atom of oil. If you recall, the plastic tubes in NOVA's neutrino detector are filled with the oil. The string of lights along the back rail represent the fiber optic cables that are inside the plastic tubes of NOVA's detector. When this neutrino collides with the nucleus, particles of light called photons will fly off. And photons are what a fiber optic cable can detect. So if a fiber optic cable lights up, it's signaling a neutrino event. With that pool table illustration, it should now be easier to understand just how those flat, white, oil-filled modules signal a neutrino event.
This is actually the only module that we've actually had to destroy. That was on our very first block, and we didn't realize that we could actually save modules. But it also gave me my only model to show you how they really work. So if you look closely here, you can see two wavelength shifting fibers.
So when a particle goes through one of the cells, a little flash of light appears somewhere in this long 53-foot tube. The light bounces around and it's white. That's why we got white siding, is because light bounces off of white stuff really well. And inside that long, thin tube is a optical fiber. The same sort of thing as you see at Spencer's Gifts in the mall, that takes the light out and sprays it out and makes it glowy. Run in reverse. The light comes in the side, rattles around in the optical fiber, and gets piped right out. And we take that light that gets piped out and put it on an avalanche photodiode. It's a sensitive electric eye that, as soon as some light from the optical fibers that are plugged into it hit it, it gives us an electrical signal, which we then amplify and record and carefully note the time and which of the thousands of tubes it was attached to, and write that out to the computer. And then on the computer we can say, all right, this tube, 50 odd feet top to bottom, saw some light at this time. And then the next layer, they're all at 90 degrees, horizontal and vertical. And so if a particle went through first one layer, it would say flash. Went through the next layer, flash. Now we know right where it went. Kind of X marks the spot. And we have many layers of that, so we can get a train of those X's and see dot, 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 dot.
And each one of these little squares would be one of the cells as it goes through. And depending on the different colors that it gives it in the pictures, it lets you know how much energy was deposited in each crossing. And so, of course, they get a very accurate measurement of exactly how many photons did they count. And then from there, they can derive how much energy was deposited.
All right. That's how the detector modules see an event and how the APDs signal that event. But of all the scientists and collaborators involved with this project, Who exactly is monitoring the detector?
So while the detector is here, it's actually really operated and run from a control room in Fermilab. And there it's monitored 24/7. And so one of the jobs that the collaborators do is there's always somebody there at the control room in Fermilab making sure that everything is running okay. This is exactly what the control room looks like at Fermilab. And so we can see everything that they can see. Fortunately, they have this screen in our way right here. But if you look really closely, you can actually see cosmic rays in real time going through our detector. So right now we're just operating the first couple of dye blocks. You can see them running the computer from here. They're actually trying to see which part of the detectors are operating well, trying to figure out where our guys should work on to fix things. And so then they communicate to our workers here and say, such and such APD is not working very good. Could you please change out that avalanche photodiode and put in a new one? This section right here is where they're installing the last of the APDs, and then we'll have the whole top of die block 4 up and running. Should have it running before Thanksgiving. So
It turns out that when a particle's energy is nearly spent, it stops traveling in a straight line and starts to curve.
And so that would be called a stopping muon. So if you're really lucky, you'll get one of these curves to stop right in your detector where you see it come to its final rest. And so you can learn a lot more from the stopping muons because you can measure the energy as it comes to rest than the ones that go straight through the detector. You don't really know what happened at the end because it's not in your detector anymore. So it's actually the stopping muons are very useful for figuring out how everything works.
And in figuring out how everything works, there are a lot of people and institutions that have a stake in how everything works. Could you explain the coordination that will take place with other institutions?
Well, the experiment itself has 30-odd different institutions, universities, national labs from all over the world, with everybody working on a slightly different facet of it. You know, my part was trying to make it trigger, trying to make it save the right data. Other people were making the electronics that read out the light, or the mineral oil that provides the material which flashes when particles go through it, or the PVC extrusions, this big giant pile of vinyl siding, essentially. Everybody seized on some small part and worked on it, and we have to all make our stuff come together as a blob which works. And so for the past, nearly a decade now, we've had meetings 3 or 4 times a year where we all sit down and update each other on what we're doing and make plans and coordinate, and then we have phone meetings several times a week too. So my students sometimes get a little annoyed because if it's not office hours and I'm expecting them, they come to knock on the door to ask me a question about class, and I'm on the phone talking to people from all over the world. But we've had a lot of practice at this in our field because all the projects are big, take forever, have lots of people, and a surprising amount of what we do day to day is project management stuff, which they don't teach you in grad school as a scientist, but we've had to learn it on the fly.
And that day-to-day project management will continue. In fact, the NOvA experiment is expected to last at least 6 years and operate pretty much around the clock.
Even though we built the detector as big as we could afford to build it, we're only going to be getting a handful of events per week. And to say something decisive about the subtle effects we're looking for, we need lots of interactions. And so we have to run for a long time, as close to 24/7 as we can manage. And the plan is that if the accelerator works as well as it's planned to, and our detector works as well as it's planned to, after 6 years we'll have enough data so that the statistics don't completely obscure what we want, right? So if you want to decide who's going to be elected president, you don't ask 10 people who they're going to vote for. You ask 10,000 people, and you get a better chance of figuring out, the error bar on that survey is, right? And so we have the same game. We want to ask as many neutrinos as possible what they're doing. That will take 6 years of running as much as we can, and we'll try to run half of those with neutrinos, and then so 3 years with neutrinos, and then 3 years with antineutrinos, and compare how the neutrinos behave to how the antineutrinos behave as they go all the way all the way up there through Wisconsin, popping out in Minnesota, and we're measuring them.
On February 25th, 2014, the final detector block was set into place at NOvA, and the pivoter was permanently secured to the floor. Once all the oil filling and APD wiring was completed, then the detector could start its 6-year data collection phase. But in thinking of this upcoming phase, I tend to reflect on a particular statement made by Professor Habig. He not only summed up the main challenge in detecting neutrinos, he also summed up what success in detecting them might mean.
Neutrinos are neutral, so they just go right through, and we don't know much about them, and so we're trying to understand this kind of last particle that is the least well known. And we think that there are clues in their behavior as to how the rest of the system of particles all fit together. It might be sort of like, you lose your keys. You find them in the last place you look, and this is sort of the last place you might look for information about particles with the neutrinos.
Well, it's time for me to leave, but it's also time for a little friend of mine to leave. I have a little neutrino friend who's thinking about leaving the Chicago area and heading for northern Minnesota.